Hello there. How's it going? It seemed like we just had a live stream a few days ago. I guess 'cause we did. It was had a live observing stream. So I hope everybody is well. Things have been a little chaotic here in Houston, as you may have seen on the news. Um, but yeah, it's it's been a week. um, so let's get into it. Let me make sure that I'm not double broadcasting or not echoing my audio back. All right. So I'm trying something new, as I always try to do every stream. Seems like I'm gonna I actually have some this wait that way. I actually have some items that I was planning on discussing today, as I mentioned in the description. First, a couple of non-sun related things. The solar or the live follow-up on the live observing session the other day. Brief comment about the Seestar update, and then the rest will be about the sun. So let's put this away for now. Oh. Hello. Hi, Alex. So the first thing is, if you tuned in for my live stream, I was trying to do two different Seestars at the same time, and it kind of didn't go as I had hoped. I was able to connect to both of them, and the problem is one of them was having like massive tracking issues, and I had alluded to the fact on the stream that I had made a last minute change. I wasn't using the stock tripod, and I had like this panorama plate. But I've just mentioned it because it might be of interest to other people. Basically what happened is at the very last minute, I removed the leveling head because there was some play in it and it wasn't leveling. So I was like, let me just remove it, put it right on the tripod. And I think I know what happened, because I put the leveling head back on just a few minutes after that long live stream, and I was able to get a photo of M13 just fine, like a minute, like 6-10 second exposures. Basically, the Seestar is an alt azimuth, so up, down, side, side. The side to side part is down here, and I think what happened is the tripod I was using, when I had it on directly on the head, it has kind of a wide base, and I think it was either applying friction to the actual bottom of the telescope or hitting these rubber kind of feet. And so it wasn't able to rotate, because I went down and I was trying to control it directly, and it wasn't moving. And I'm like, oh, and luckily I didn't burn out the motor, but that's a cautionary tale. Make sure you have enough clearance on your telescope when you're doing that kind of thing. So next, hold on. Next, we have the Seestar update. This just came out the other day. There was a Seestar update after the live stream, and it had some hold on. It had I took a screenshot of the release notes, and it was interesting. So someone had just asked in the comments of how to download if they had an iPad, how do you get to the subframes? And there was unfortunately I don't have my phone set up to screen share, but basically there was a way in the album where you could go in the well, actually, let me bring it up real quick. I'll bring up the iPad version. It won't have anything to connect to. But if you go into this My Album part, and if you have the Seestar connected, you can go click on the Seestar and or on this thing, it'll have your Seestar there, and you can go look at all of the targets you took, photos of that are on the telescope, and the subframe directories, and you could go in and you could click on an item and you could share it or download it, but it only allowed you to download one at a time. But this update fixed that. It allows you to multi-select download. But the one thing I did notice, I only briefly looked at it, maybe other people will have a different experience. It seemed like it only downloaded, when I went into the subframe directory, it looked like it only downloaded the JPEGs to my directory. Maybe the fit files are there somewhere, but I didn't see them. So I need to look at that further. So that still kind of interferes with the ability to be able to use like a wireless workflow or one involving like an iPad. So I think you'll still have to connect it to a computer and download the subframes. It has the new release has some additional ability to share saved files, Korean voices, zoom button in Sky Atlas. This one was kind of, I guess I can see that it was okay. Yeah, it's fine. But in here, I haven't brought up the Sky Atlas in this instance. So please, okay. So it's got, so this is what it added, this plus and minus here. Whereas before you could, actually, this is interesting. This might have actually helped me. So when I do it on the phone, I can pinch to zoom in and out, I believe, because I'm pretty sure that's how I've used it. But when I'm using it on the iPad, I mean, when I use the iPad version on my laptop, like the pinch gesture on my laptop isn't doing anything, but this would actually allow me to zoom in and out. So actually that would help me because of this particular workflow where I'm running the Seestar app here on my Mac laptop and the gestures aren't working correctly. So I guess that's fine. And then increased sun and moon tracking range. I'm not 100% sure what that means. My guess was it, like if the sun or moon are too high in the sky, it might have a problem, but I don't know if that's what that means. Because at least here in Houston, the sun's getting really close to the zenith at times. So I wonder if that might help with that. And then some of these other things are just optimizations and bug fixes and stuff. So yeah, so that was that release. I don't know if anybody else has had a chance to play around with the new release. But what else? So that is that. So now to the sun. This live stream might be a fairly quick one, but depending on how things go, and how much I end up discussing it. But yeah, so as it probably everybody knows or heard, there was quite an event last week with the sun, where the aurora were visible in areas that historically have never seen aurora before. And I kind of wanted to discuss that a bit. Not just kind of the aurora, but kind of what happened and not so much my experience with it, because my experience with it wasn't as interesting, because unfortunately here in Houston it was a bit cloudy that evening. So one thing I did is I I knew that the sun had been pretty active. I mean, we're at a solar maximum, and so there had been a lot of sunspots, and in particular, I had seen this sunspot group, and I took this photo on last Friday during the day. It was sunny during the day, and then clouds rolled in the afternoon, just in time for the aurora. But this sunspot group, this particular sunspot group, is that I pointed to in the thumbnail. This is the thing that hold on a second. Sorry. Okay. Yeah. This is the one in particular that caused the issues, and or not caused the issues, but that caused the fireworks show, as it were. And so I don't know if you probably heard about it beforehand, and I kind of wanted to go into, well, I want to talk about what happened and how what was predicted, and so on. So what happened was this sunspot group caused a coronal mass ejection, which is basically a giant kind of a mass of plasma and magnetic fields kind of tied up in it that get ejected from the sun at a pretty high rate of speed. The average mass of a coronal mass ejection is like over 1 trillion pounds or kilograms, either way, take your pick. And they typically take 1 to 5 days to reach Earth orbit. Now, they don't hit Earth necessarily, depending on which way the sunspot is pointed, but that's kind of the setup. And because of the magnetic fields that are in that plasma and the charged particles, when it hits Earth's magnetosphere, if it's pointed at Earth, when it hits Earth's magnetosphere, it causes it to kind of compress and extend. The charged particles come in at the poles typically, and when they hit the upper atmosphere, they cause ionization, and depending on whether it's oxygen or nitrogen and how it ionizes it creates colors like blue or green or red, which is why the aurora have those colors. Now, sometimes the coronal mass ejections, remember I said it takes 1 to 5 days to reach Earth, and usually it's believed they're constrained somewhat by the speed of the solar wind. But if there are a series of coronal mass ejections, the initial ones kind of clear the path for the subsequent ones. So some of the later ones can potentially reach Earth much quicker. And I think that's partly what happened this time. Also, if you notice where this sunspot group is, it is not actually pointing directly towards Earth, but this is where things get a little kind of oops, wrong window. This is where things get a little kind of interesting, and I am by no means an expert in solar physics, nor do I play one on TV, but I thought it might be of interest to people. So basically, oopsie, wrong one. This isn't, which window am I supposed to be on? Okay, here we go. Okay, so see this. This is, so I'm going to go through a bunch of things. So this is just a photo of a prominence, which is kind of, some of them kind of they're not necessarily coronal mass ejections. It's just some matter getting shot up from the sun that then kind of collapses back onto the sun. Now, in the case of this is a satellite view, this image right here of a coronal mass ejection. The kind of like scattered kind of static there are charged particles hitting the photo sensor. And this is one from 2021. But you can see basically mass getting shot off from the sun. And there's like this little disk that blocks the brightest part of the sun. So that was kind of the setup here. Now, what's interesting is because of, like I had mentioned, that sunspot wasn't pointed necessarily directly at us, but the sun's magnetic fields kind of get twisted around as the sun rotates, and it's something called the Parker spiral. And so they were saying even as the sunspot kind of approached the edge of the sun a couple days later, that there was still a chance that it would produce a coronal mass ejection that would hit Earth because of this spiral, that it can actually magnetically get curved back to Earth, which is kind of interesting and kind of a little disconcerting too. But so this one in particular, coronal mass ejection went, let me just see. Yeah, so how did we kind of measure it, and how did we know that it was, like, if you were kind of looking around online, like earlier that day, they were talking about how there was this prediction of like it was going to hit Earth. And how did they know that? Well, it turns out that we have a lot of satellites in orbit that their task is to just monitor the sun all the time. And a couple of them are interesting of note. One of them is SOHO, this satellite. It was launched back in the 90s. So it's been out there, 1995. So it's been out there for 28 years. And it's in kind of this Lagrange orbit, where it's basically kind of midway, well, not midway, it's about 1 million miles sunward from Earth. And it's kind of balanced between Earth and sun. And the nice thing about that is if a large coronal ejection comes from the sun, we'll know, based on some other things I'll get to from another satellite, that something's headed towards Earth or might be headed towards Earth. But you don't necessarily know 100% for sure. But this satellite, because of its position about 1 million miles sunward in this L1 Lagrange 1 position, it's actually able to detect the passing plasma from the coronal mass ejection and give about a half-hour warning if things are particularly bad. Now, they generally kind of know a bit further ahead that it probably is heading towards Earth, but then they can really kind of get a more accurate idea. But how do they know well, they know to look out for it, but then there's this other telescope called the Solar Dynamics Observatory that's orbiting closer to Earth, but it's a more recent satellite, but it produces all these. I'll include links to all these if you want to look at them, because it's kind of interesting, especially if you. I'll get into it later, but if you want to do like solar astronomy, this is actually kind of an interesting resource because you can kind of get an idea. Like, so this satellite, it's observing the sun in multiple frequencies, ultraviolet, different frequencies of ultraviolet plus visible. And so it has like all these very unique views, and like here's a view. And so you can see the prominences, and so what happened last week is this satellite here, the SDO. Let me pull this up. Oops. Just renamed a file. Yeah. So you can see, let me close this window. You can see from the Solar Dynamic Observatory that in one of the frequencies where that sunspot was, you can see this bright flash of light. And I think this is in some ultraviolet band, or maybe even X-ray. Probably ultraviolet. I don't think it's X-ray. Never mind. Scratch that. I think it's, anyway, that bright flash indicated, you know, there's a major flare slash kind of eruption going on the sun. And it was that region 3664. And so we kind of knew that it was coming. Now, what's interesting is there's all these resources out there that you don't necessarily, that you may or may not be aware of. Like you can look at the live satellite data, or the most recent satellite data from that Solar Dynamic. And then like NOAA, the U.S. government, National Oceanic and Atmospheric Administration, they have a space weather prediction center. And so they're always all over this kind of stuff. And so they had like an article about, you know, these X-class flares that were happening on the sun that were probably going to lead to aurora. And so you have the one telescope, or the one spacecraft that's monitoring the sun in multiple frequencies. And then you have the SOHO satellite, which is kind of parked midway between, or not midway, parked 1 million miles sunward from Earth. And I forgot to mention it, the going back to that Lagrange point, another interesting thing, this L2 point here, that is actually where the James Webb Telescope is parked. By the way, I'm not sure if you hear it on the microphone, but there's another thunderstorm going on outside. So if we have any power issues, the stream might have a problem. So if it ends, or if it hiccups or just ends suddenly, that's what happened. Hopefully not. Anyway, so moving on. So you've got those two satellites that are kind of feeding information in, and then you have this NOAA space weather organization, and they do all kinds of things. Like they look at one of the side effects besides the aurora is it can cause certain kinds of what do you call it? Certain kinds of radio frequencies to go to basically have problems, to interrupt radio frequencies. It can also cause satellites to fail. It can cause other things, which hopefully I'll be able to get to without. But yeah, so from last week, I kind of was looking at these websites, and like they had these projections, or these were based on estimated, basically things were going crazy with the different instruments and stuff about like measuring like proton flux and X-ray flux and stuff. It's kind of interesting. But then one of the things that this satellite that the space weather agency does, or division does, they did aurora forecast, and I took a shot of it that evening, and so you can kind of see, you know, everything kind of looks, you know, okay, but then this was a projection, maybe an hour out or something of basically what was going to happen with the aurora. And it ended up going even further south than it did, or than they projected, which was, the projection just seemed kind of unreal, but it actually ended up even more than that. So that's kind of what happened, and what some of these spacecraft and government, different organizations were doing. Now, yeah. So that is, sorry, going back to, oops, let's go to, so past events. So this is where things get a little interesting. Depending on if I don't know, a lot of people may not be aware of this, but there have been other incidents over time. Like, this was a pretty strong flare, but these kind of flares, or these kind of geomagnetic storms, they can cause problems. They can cause problems on Earth. Like, there have been in 1989, basically because of the magnetic fields, and when they get down to Earth, they can, or to ground level, they can induce power on long cables, like power cables. And so it caused a cascading failure in Quebec in 1989 that knocked out power for like 9 hours to millions of people. And there was an incident in 1972, knocked out a satellite and caused some other ones to kind of have issues for a bit. It actually even detonated some mines, like in the water. In 1921, there was an incident, that a geomagnetic storm that actually caused caused electrical fires with telegraph lines. And kind of that's interesting. I'm hearing, like, I'm not sure if you heard the thunder on the stream. We'll see if this lasts. Unfortunately, most of the stuff is plugged into a UPS, but I think there's one thing that isn't. Anyway, the big one is the Carrington event, which was named after, it was kind of the granddaddy of recorded events. It was in 1859. So it was, a few decades after the Messier catalog. So it was kind of getting into more modern astronomy. They had telescopes. They were keeping good records. Astrophotography was not really a thing, or barely a thing. But there were sketches. And so Richard Carrington, he drew a sketch of this sunspot group, which looks kind of weird, but it was on the sun, and he actually saw like a flash of light, which normally those flares are not visible they're not visible in white light. They're visible like in the ultraviolet. They're not normally visible like through white light. But there was one recorded, and about 17 hours later, the aurora started on Earth. And remember I said 1 to 5 days? The fact it took 17 hours, they think there had been an aurora, some strong aurora like a day or two before, and they think that kind of cleared the path. So then when the Carrington flare happened and caused the coronal mass ejection, that it was able to reach Earth in only 17 hours, because he recorded the time when he saw the white flash on the sun. And so we know, going back and knowing how these things work better, like what happened and how quickly it happened. And that works out to be about 5 million miles per hour, which is a lot faster than the solar wind. So it had to have had something cleared out in front of it. And it was truly exceptional. Like, these aurora were impressive, but the Carrington event, people supposedly could like read in the northeastern US at night by the aurora light. And the aurora were visible as far south as Colombia. So like that's only a few degrees from the equator. This time I saw things down in the like Puerto Rico reports of aurora from from last week, but it was even further south during the Carrington event. But the thing that has been troubling to people is the other things that happen. Now, it was kind of getting into the more modern era where you had telegraph lines. And so you had these long cables, which didn't exist in previous eras when there had been strong geomagnetic storms. So we don't know how to compare them necessarily. Well, the telegraph lines, it caused fires. It shocked some of the operators. And in some cases, the operators were able to actually disconnect their batteries, and the induced current for several hours was able to run the telegraph line without any external power being added to it. And so the concern kind of, you hear mention where they talk about a Carrington class event. The concern is that a similar flare happens, but with our modern computers and electronics and satellites, that it would cause issues. And when I say issues, like some of the projections were, it could cause like hundreds of billions or trillions of dollars worth of damage to electronic infrastructure globally, which would be catastrophic. But what's interesting, so in 2012, there was a coronal mass ejection that they think might have been comparable to the Carrington event that missed Earth. So yeah, that's kind of the concern. But then this one that happened in like the last week was a very strong one. And so yet there weren't any reports of outages. So it's unclear, like, was there something different about the Carrington event besides just its strength? Like maybe the magnetic fields, well, no, they measure. Anyway, it's kind of interesting. Now we're getting better at, like, because they know that these things happen, like people who design like long distance power cables and satellites. So things have gotten more hardened. So maybe things won't be as bad, but it's still a big concern. And another fun thing about it is, whenever these solar events happen, or just the solar kind of, when the sun's more active like it is now, it causes Earth's outer atmosphere to expand a little bit. And that can actually cause premature reentry of satellites, which happened to some SpaceX satellites not that long ago, like a year ago or so. Or at least that was what what was blamed for the premature reentry. So what? Oh, and the other interesting thing, since we know about these events, we have we're able to, and there's sensors on our different space probes that we've sent out. We're able to detect them, even like probes on Mars, probes and satellites or other spacecraft on and around Mars have detected coronal mass ejections as they go by. And even the Voyager probes have detected them like months after they were ejected, and they finally got that far out from the sun. They were able to detect the flux change as they go by, which is, I find, really kind of interesting. So this has all been kind of, let me make sure that there isn't. Oh yeah. And so like there's these other websites. I'll include links to a bunch of them, like Space Weather. They kind of collect a lot of a lot of information, which is kind of interesting. Um, but so now in a less, so now what? The future. um, so what's kind of interesting. So I'm gonna kind of keep it in space for a bit, and then I'm gonna bring it back to Earth. Um, what's interesting is so this big massive sunspot group has now rotated off around, where we can't see it anymore. But how do we know how it's doing? We don't have any space probes that are kind of like further away from the sun. I mean, like, I think there was a proposal I believe there was a proposal to put a space probe at L3, or kind of a modified L3 orbit where it's kind of in a halo orbit around L3, so you could actually look, so it could image the far side of the sun, but it would have to be in a halo so it could still radio back to Earth, because otherwise if it was in exactly on the opposite side of the sun, it would be the sun would be in the way and it wouldn't be able to send radio waves. And fun fact, this is where Bizarro Earth is. No, not really. But this is on the opposite side of the sun from Earth. So how can we keep track of things? Well, this is where things kind of get interesting. And I kind of had heard about this, and I kind of was, and it kind of, this jogged an old memory. But this is the Solar Dynamic Observatory website. And so like they have all these different things, and they have like magnetograms and colorized magnetogram, and like, but then you get to like, and Dopplergram, and then you get to this thing, this AR map. And it's like AR is active region, but it looks like, a projection of a sphere, like Earth maps, that's what this is. But the funny thing that you kind of notice is it shows all of the sun. Well, how is that possible if we can't see the opposite side of the sun? Well, back in 2000, there was this technique called helioseismic holography, which basically, by measuring certain properties of the front side of the sun facing us, we can determine active regions on the other side. It's kind of interesting and kind of weird, but it was interesting looking at, I think it was it this movie? Let's see if this loads. What day? Yeah. So let me stop this. So what's interesting is, here's the 7th, and this is that. Is that right? Yeah, this is that very active sunspot group right here. And you see, as it kind of rotates out of view, it still shows up on the on this active region map of the sun. So they're able to kind of see how big it is roughly, even after it's kind of rotated out of view. So if it kind of shrinks, they'll know once it comes back around, it's not going to be as strong. And if it stays the same size, they'll kind of know what to expect. But I found that kind of interesting that they were able to kind of figure out the here's some more stuff about the far side images using the seismic signature of magnetic activity. Yeah. I mean, it's interesting. So from a practical point of view, they're able to kind of do predictions. They're observing the sun in multiple frequencies, but they've gone further, and we can measure or get a rough idea of what's on the other side of the sun. So we'll know kind of when there's a big sunspot group that's maybe about to rotate into view, and so we should be kind of prepared. So yeah, that was kind of interesting. And I did promise that I was going to bring this back to Earth, and I am. So how does this actually kind of let me close out some windows here. I've got all my little images up here. Let me see. Let me go check. Okay. So how does this kind of helioseismology. So let's bring it back to Earth. So I started off this live stream showing kind of a photo I took in white light of the sun, and that's all well and good, but as you look at, oops, wrong window. If you look at like this SDO, the satellite view, there's a lot of other things, a lot of other ways to see the sun, and they all show different things. Now, obviously, they have an unfair advantage because this is from a satellite that's outside of Earth's atmosphere. But what kind of things can we do within Earth's atmosphere? Well, one of the most common ones you get are, besides white light photos, is you can do hydrogen alpha, which is a specific narrow band that's in kind of the red wavelength. And I believe I had mentioned that there's these telescopes typically have been expensive, but like the really like thousands and tens of thousands of dollars, but like, I mean, this one, its MSRP is $900, but you can sometimes get it for cheaper than that or used. But it's so this is a hydrogen alpha telescope, and so there's other things that people do, like, or other frequencies, like there's calcium line and sodium line, and some of those that they see different layers of the sun. So the nice thing about hydrogen alpha compared to white light, you can see the sunspots. Let me just pull up the example. So, with like the Seestar, you take a white light photo and you can see kind of some level of granulation a little bit. With a higher resolution telescope or camera, you can see more granulation, and you see like the sunspots. But that's about it. But if you get a hydrogen alpha telescope, like the like that one I just showed, you can start getting exposures like this, where you can start seeing kind of more detail. Now, granted, this was taken with a very low resolution camera. It's a ZWO like guide scope. It's not the highest resolution, a cheap guide scope, but it's still kind of interesting. And you can see, like these are called filaments, and they're actually kind of prominences, like those things out the side, but it's when they're above the surface. And you can see these other kind of things, and now you kind of see like a little protrusion there, but you can't see the details. Now, the thing about doing hydrogen alpha is it's got like its own set of software, and so like FireCap, it's some of it's similar software to what you use for planetary imaging if you're using like a dedicated planetary kind of setup with, or if you're using like a planetary camera and, kind of, I'm not talking about like doing it on the Seestar, but like if you have it on a different, standalone telescope, like if you build your own rig. And so like with FireCap, it's got like all these controls where you can kind of, it's taking multiple frames a second, and you kind of can adjust the histograms and see. Here you can actually see the prominence, and it'll record the video, but then you can, the software will kind of, you can have it pick not this software, but like some of the other software, you can, when you stack it, you can basically do lucky imaging where you take the clearest frames and it combines them and to bring out more detail in the sun. And I'm just getting started with that, but it is kind of interesting. And this is, when you process it, this is like just, this isn't stacked. So it's still like super noisy, but it was kind of satisfying being able to actually see all these details and also the prominences at the same time. Whereas normally you have to kind of overexpose to get both. But like I say, this was a really noisy image, but still it's kind of interesting, and it's kind of a nice way to extend the hobby into the daytime. But it requires, unfortunately, dedicated equipment or a special kind of filtered eyepiece, which costs over $1,000, the Quark. But it's kind of interesting, and it lets you kind of see prominences, not just during eclipses, and you can see kind of how active the sun is. Like while I was doing this over a couple hours, this particular prominence right here. Oh, I'm not even showing the computer screen. Anyway, yeah. So anyway, this is the software I used, and here's the prominence. And this, I saw a change over the course of like an hour or a couple hours. Like I saw it was initially brighter, and then it kind of started dissipating. So it's one of the interesting things about doing this kind of photography of the sun is you appreciate how rapidly changing the sun is. And since I don't think I had this on screen, here's the single frame I processed where you can kind of see the sun itself and or the disk, and you can see kind of the filaments, but you can also see the prominences here. But it, like I say, this was unstacked, single frame. It's super noisy, so I'm just leaving that off. But yeah, that's kind of an interesting thing if you want to get into a different aspect of the hobby of astronomy and do it's interesting. And I'm debating doing some live observing solar stream. I don't want to completely do just live streams on this channel, but I might be doing that. And another thing, both from a solar observing point of view and just kind of potential aurora point of view to be aware of, is the solar maximum may not happen till next year. So that's not to say we will have anything as spectacular as last week, but we could have some more things, some more events happening where, hopefully not a Carrington event, but we might have more solar flares that produce exceptional aurora. But only time will tell on that. Let me go back to the primary view. So yeah, I don't like belaboring the point, so I think that's all I have. Like and subscribe as always, and if there's sorry, just looking at things. If there's any other topics you want me to cover, or please let me know in the comments. I would be happy to do something about it, talk about a variety of things. I have a lot to talk about, but anyway, I think that is it for today. So thank you for joining. And if you're watching this on replay, I will probably be putting a description with the time codes. I usually update the description usually within a day or so of this live stream. So in the meantime, I think I hope you're having clearer skies than I do, and have a good rest of your day or evening. Yeah, so I hope you have a good rest of your evening, and thanks for watching.